Alright, so here we have question number 7. Figure 7.1 shows a horizontal current carrying wire PQ in the gap between the poles of a permanent magnet. So this is from the topic of force acting on a current carrying conductor placed in a magnetic field, as it is from that topic. And you are given with the diagram. You had the North Pole here, just ignore the annotation and the drawing. North Pole here, South Pole over here. Then you have the current carrying conductor. The current is flowing to the right side. The direction of the magnetic field is upward, that is from north towards the south. There is a magnetic field in the gap between the north and the south pole. Yeah, it should be. The current in PQ is from left to right, so current is towards the right side. Describe the effect of magnetic field on PQ. So whenever you have a conductor which is placed inside a magnetic field and the conductor is carrying the current, a force acts on that conductor. So for 1 mark you write this thing: the force acts on the conductor, or the conductor PQ experiences a force. Then for the 2nd mark, since force is a vector quantity, then you need to come up with the direction of force as well. And the direction of force is to be calculated by the by the left hand rule, Fleming's left hand rule. You stretch your 3 fingers in such a way that they are perpendicular to each other: thumb, forefinger, and middle finger. The forefinger has to be upward, right? The forefinger has to be upward. The middle finger has to be towards the right side, and whatever the direction of your thumb is would tell you the direction of force. So in this situation, if you apply the left hand rule, your thumb would be pointing towards your body, would be pointing towards you, and with respect to the piece of paper, the thumb is pointing outward, so the direction of force would be outward. So the thumb is pointing something like this. It's difficult to draw outward over here, so I'll just represent like this. The thumb would be pointing towards you, so the force has to be outward. This is how we use left hand rule, sorry. State the effect of PQ on increasing the strength of magnetic field in the gap. Effect on PQ on increasing the strength of magnetic field in the gap. If you increase the strength of magnetic field, the force acting on the conductor would be increased. So what you can write is the force acting on the conductor increases. So it would be moving with greater speed. It's better to say speed of movement. And it would rotate if it is in the form of coil, otherwise it'll just move in a straight line. So the speed of the movement increases. Yeah, that's better. Or there's more force. You can also say there's more force, there's more acceleration, there's more speed. Anyway, moving on to the next one. 7.2 shows a part of our torch. The torch does not contain a battery. Okay. The torch is shaken, and this causes the magnet to move forward and backward and forward through the coil. Explain why an EMF, electromotive force, is induced across the coil when the magnet moves. So this one is a standard question of electromagnetic induction. What they're saying is there's no battery, then how come EMF be induced in the coil? A standard textbook question of induced electromagnetic induction. So what happens is, as a concept we study, whenever there is relative motion between the coil and the magnet, there is rate of change of magnetic field, and due to which EMF is induced. For every question like this, you can write down the same 2 sentences. There is relative motion between the given things, which in this case is between the coil and the magnet. One of them has to be magnet, and the second one is obviously, generally it is coil, but coil can be in different forms. So whenever there is relative motion between the coil and the magnet, the magnetic field enables the coil to cut the magnetic field, thereby inducing EMF in the coil. Or, alternate explanation, due to the relative motion between coil and the magnet, there is a rate of change of magnetic field through the coil, and that induces EMF in the coil. Say one way to increase the EMF, induced EMF. If you move the coil faster, if there is increase the speed of relative motion between the coil and the magnet, or move magnet faster, or if you increase the number of coils, number of turns on the coil, or if you increase the strength of the magnet, use a stronger magnet. So there are at least 2 to 3 ways in which you can increase the induced EMF in the coil. As the magnet moves in the coil, the induced EMF produces current in the coil. Explain how this opposes the motion of the magnet. So this one is related to the Lenz's law. According to that one, whenever EMF is induced in the coil, the EMF would be induced in such a way that it would try to, you can say, oppose the cause of its production. So if you're moving magnet towards the coil, the EMF would be induced in the coil, and due to which there would be current, and the direction of that would be in such a way that the coil makes a north pole over here and a south pole over here, if you're trying to bring the magnet close to the coil. And because only then the coil can oppose the magnet. So it's basically whatever you're trying to do, the coil will try to do the reverse of it. If you're trying to move the magnet away from the coil, then the coil will try to attract the magnet towards it, and in that case there would be south pole over here, north pole over here. Only then the coil can attract the magnet. So whatever we're doing with the coil, whatever we're doing with the magnet to the coil tries to do the opposite to the magnet. This is the Lenz's law in simple words. So you can write it down like this: current carrying coil produces magnetic field, and then magnetic field in such a way that the north pole is induced on the right side in front of the north pole of the magnet, and the south pole is induced to the left side. So north pole over here, south pole over here. Only then it can oppose the motion of the magnet. Then we have question number 8. Figure 8.1 shows a circuit containing 230 volts AC supply connected to a TV and 2 lamps. In normal operation, both switches are closed. The power supply to each lamp is 40 watts, and the power supply by the to the television is 120 watts. Calculating normal operation, the total number of kilowatt hours of energy supplied to the circuit in 1 hour. So kilowatt hours you need to find. In order to find kilowatt hours, you need to find first kilowatts, and then you need to multiply by the time that should be in hours. So since it is 1 hour, so that won't make any difference. Whatever the value of kilowatts is, the same would be the answer. Now the thing is, we need to calculate the number of kilowatts, and for that one, 1, 2, 3. All 3 of them are connected in parallel. What do we do when 2 devices are connected in parallel? What is their total power? We add them. The total power is added. For example, you have 40 watt bulb here, 40 watt bulb over here. What is the total power? If you were using a single one, it would have been 80 watts. So what do we get from here? 40 plus 40, 80 plus 120. We get 200 watts. If you convert it into kilowatts, that would be 0.2. You multiply by 1, you get same 0.2 or 0.20 kilowatt hours is the answer for the first one. In the second one, you need to find the current in each lamp. Power is given, voltage is given, you can easily find the current. So you see, what is the voltage across this lamp? It is connected in parallel with this AC supply, so the voltage across this one would also be 230. Voltage across this one would also be 230. Voltage across this one would also be 230, because all of them are connected directly to the power supply. And what is the power? Power is 40. The formula that relates power, voltage, and current is P equals to V times I. You can easily find I from there. And how do we do that? Like this. I equals to P over V. Power was 40. Voltage is 230. You divide it on the calculator. You get 0.17 into significant figures. Amperes, the unit is already written. Then we have the next one. Explain why the switches are placed in the live wire and not in the neutral wire. A standard question, whenever you get a question like this, you write down the same statement. Because we place the switch in the live wire, so we have the control, so the high voltage wire can be disconnected from the appliance when the switch is turned off. So when the switch is closed, it will prevent the lamp and the TV from being at high potential, that is 230 in this case. If you place it in the neutral wire, even if the switch is closed, the live wire will still be connected to the appliance. State one advantage of connecting the two lamps in parallel in this circuit. Standard advantage of the parallel circuit of parallel connection of the appliances is if one of the appliances is out of order, the other one would still be operational. So if one bulb fuses, the other one would still be working. Alright, moving on to the next one. This is the second last question from here. Figure 9.1. Figure 9.1 shows the main parts of the nuclear reactor, which undergoes a fission reaction for the production of the electricity mainly. The fuel rods contain uranium-235, which undergoes nuclear fission. Describe the process of nuclear fission that occurs in the fuel rod. Your description should also include the role of neutrons in the process. So the fuel rods basically are made up of uranium, because our fuel in that case is uranium. So during the process, what happens is neutrons would be absorbed by the uranium nuclei. And in that process, so this is your uranium nuclei, these are the neutrons. The neutrons, they bombard the uranium nuclei, they hit the uranium nuclei, they are absorbed by the uranium nuclei, and they are converted into daughter nuclei. And with that one, there are more neutrons emitted. And then every other neutron further strikes to the uranium nuclei and split them into smaller nuclei with further emission of neutrons. So it is a chain process, but for the nuclear reactor we try to control the chain process. Otherwise, if it starts, it would be very difficult to control it, because the reaction would just it would take a snowball effect. The reaction would start getting bigger and bigger until it gets out of the hands. Explain what happens as the control rod is moved out of the reactor core. So these are your control rods, these ones. So if you're moving the control rods out of the reactor, more number of neutrons would be striking the uranium, and has more nuclear fissions would occur. So since there would be lesser number of neutrons that are absorbed by the rods, hence there would be more number of neutrons available for the nuclear fission, and hence there would be more nuclear fission reactions. Then you have the other one, part C. The nuclear reaction releases energy at a steady state. I was saying it is a chain process, so the energy increases exponentially. So let's say, just for sake of understanding, for the first reaction the energy was 1 joule. For the second one it might be 30 joules, then it might be 300, and then it might be, let's say, 10,000, and then it could have been 5 into 10 to the power 10 joules. So this is how the energy would increase. It increases exponentially. But in this case, for the nuclear fission reaction, we control the amount of the fission reaction. So by referring to the neutrons, describe what is happening to achieve this steady state. Like I said, when one neutron strikes the uranium, it breaks down into two smaller nuclei with further emission of neutrons. But what we do is we ensure that only one of the neutron would be used further, and the rest of the neutrons would be absorbed by the rods. So this is how we ensure that a steady state is reached. So on average, only one neutron produced by fission to cause another nucleus to fission. Part D. Explain the purpose of the moderator in the nuclear reactor. So moderator, you can see over here, these are the moderators. So what they do is, these moderators, they slow down the uranium, they slow down the neutrons. And once the uraniums are slowed down, they are not in a hurry, they have more chance of being absorbed by the nucleus. And if they have more chance of being absorbed by the nucleus, the reaction would be faster, there would be more fission reaction. Alright, so question number 10. The sun is a star and is in stable part of its life cycle. Using ideas about forces, explain how the sun remains stable in this part of its life cycle. So the sun has been there for like 5 billion years, and it would remain there for the next 5 billion years. And right now the sun is in the stable state. What do we call that? We call this state, or this stage, as main sequence star. So right now the sun is a main sequence star. This is what we study in the life cycle of a star. We explain all of these stages and all of those processes in detail. In the main sequence star, the sun or any other star would be in a stable phase. And how does it remain stable? Because the two forces, one is the gravitational force that tries to compress the star towards its center. So there's an inward pressure which is balanced by an outward pressure which exists due to the energy or the high temperature or the heat released by the nuclear fission. And these two forces match out, these two cancel out, and the sun at this stage neither expands nor contracts. It remains just like it is now. So it remains in the stable phase. Then we have the next one. Describe what happens to the star of similar masses to the similar mass to the sun at the end of the stable part of their life cycle. So the stable part was the main sequence star. And after the main sequence star, the sun or any other star would start losing out or start running out of the hydrogen, and they start undergoing the fission using higher elements that you see on the periodic table up till iron. And in this case, because they are using higher elements for fission, the energy or the force produced in consequence would expand the star, because that force would be much greater than the gravitational force that was trying to compress the star. So the star would expand. It would become a red giant. If it were many times bigger than the sun, it would have become red supergiant. But for the stars of the size of the sun, they become red giant. And once the star ejects the outer layer of dust in the form of planetary nebula, it becomes a white dwarf. And the white dwarf keeps releasing the energy, and once it has released a significant amount of energy, it becomes a black dwarf, which eventually vanishes. Alright, part C, we have orbital speed of the Earth around the Sun is 30 km per second. Use this value to calculate the distance of Earth from the Sun. Show your working, state the unit of your answer. This formula for the orbital speed is this one. Where do we get it from? We get it from speed equals to distance over time. But since the distance is in the form of a circle, that would be the circumference of the circle, which is 2 pi r. R being the distance between the Sun and the Earth, which we need to calculate. The speed of the orbital speed is given as 30 km per second. We can convert kilometers into meters, and that'll be 30,000. The time period, the value of time period is 365 days, because it takes Earth 365 days to travel or to orbit around the Sun. So 365 days, but we have to convert it into second. 1 day we have 24 hours, 1 hour we have 3600 seconds. Divided by 2 pi, you hit it on the calculator, you get this thing. You get this thing, you write in two significant figure, you get 1, 5 followed by 10 zeros. Then you can write in standard form, that would be 1.5 into 10 to the power 11 with the unit meters. The light is emitted by the distant galaxy. Now shows various amount of redshift. State the name. State the name of the galaxy that contains our Sun, Milky Way. Fact-based question, you have to memorize it as it is. What is meant by a redshift? As a galaxy is moving away from us, its wavelength increases. The wavelength appears to be stretched, or frequency, you can say frequency decreases. So as the source of light moves away from us, in this case the source of light is a galaxy. As the galaxy is moving away from us, its wavelength, the wavelength of the light emitted by the galaxy appears to be stretched, appears to be longer. This is called redshift. So how is it caused? As I mentioned, when the galaxy is moving away from the observer. Who is the observer? The scientist here on the Earth. We are the observer. So as it's moving away from the observer, it appears to be stretched, or the wavelength appears to be longer. Then we are comparing, an astronomer compares the spectrum of light emitted by the Sun with the spectrum of light emitted by distant galaxy P and Q. Figure 10.1 shows the same 4 lines are observed in the 3 spectrum. So this is the standard one that we are comparing the next 2 galaxies with it, galaxy P and galaxy Q. You see these the spectra of the galaxy P, the lines of the galaxy P are slightly redshifted. How do we know? Because the wavelength increases on this side, and for light, red is a color which has more wavelength, so it is getting towards the reddish side. The hint is over here, increasing wavelength. So wavelength is increasing means your galaxy's P is getting redshifted, but meanwhile the galaxy Q is having, the light from the galaxy Q is more redshifted because it's more towards the right side. Then you have State what enables the astronomers to deduce about galaxy P and galaxy Q. Explain astronomers' reason in your answer. You see, in the galaxy Q is more redshifted. The lines are more towards the right side. So light from the galaxy Q is more redshifted. Hence, the galaxy Q is moving faster. Also, Q is further away from the sun. As further away the galaxy is, the faster it moves. So this is what we study in theory, that if a galaxy is away from us, it would be moving, the light would be redshifted, and it will be moving away from us. But if a galaxy is even further, alright, even further than the previous one, now this galaxy would be receding. Receding means moving away. That galaxy would be receding from us even faster than the previous one. The further away it is, the faster it recedes from us. So this is what we can deduce from here, that the galaxy is further away from the galaxy P. The light from the galaxy Q is more redshifted, and the galaxy Q is receding faster than the galaxy P.